Electricity and magnetism, whether it's an electric field or a magnetic field, it all kind of depends on your reference frame. They're really aspects of the same thing. And this is why we call it electromagnetism. It's really one thing. It's not that there are electric fields and there are magnetic, and a completely different thing is the magnetic field, or that there are electric forces and unrelated magnetic forces. They are the same thing. It's all a matter of the reference frame that you're in, which description you use.
Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
Lecture 111, titled The Relativistic Origins of Magnetism. And I could have called this electromagnetism. I could have called this the Lorentz force law. A lot of different titles, but this is the one I went with. I want to describe an experiment in which I have two wires hanging. Don't worry about where they begin and where they terminate. The point is that let's assume that there is a current flowing in these wires. We'll call this wire 1, and we'll call this wire 2. We'll call this current 1, I1, and we'll call this current I2. And we're going to assume that these wires are in every way possible identical, and that the current is identical as well. And we're going to talk about different frames of reference. But first, let's remember what's going on inside a wire that has a current. If the current is going this way, which direction are the electrons, the conduction electrons, going in the wire? Are they also going up?
Yeah.
No, they're going down. If the wire was some other material and the charge carriers were positively charged, then the charge carriers would be in the same direction as the current. So we have some conduction electrons which are going in the opposite direction in both cases. I'll just write E minus. And they're traveling with a velocity, a constant velocity, we call the drift velocity. Some further considerations regarding this current. It's a steady state current. So what does that mean? Well, that means that the current is not changing in time. So it's at a constant current, like 1 amp or 2 amps, whatever it is, 10 amps. So remember that conductors are special materials. If I were to introduce an external electric field into a conductor, the free electrons in that conductor would move in such a way as to cancel that electric field out.
Yes.
Well, when we hook a wire up to a battery, it's a little bit different, okay? There is, in fact, an electric field inside that conductor. It's what is causing the electrons to move with this drift velocity. And so if we were to look at it initially, like I hooked the battery up in the wire, here are the conduction electrons, what do? Well, they immediately start to accelerate.
Okay.
But I said the drift velocity was a constant velocity. Where's the acceleration, right? This is all statistical. It's averaged over time. Because they're accelerating, banging into stuff, stopping, or maybe reversing direction, and it's on average you have this constant drift velocity. Okay, but we're not going to worry about that. We will assume that the current is in fact moving like a little train, right, along at a constant rate, and the drift velocity of the electrons is a constant, and the electrons are just marching one by one in a nice line, right, in the opposite direction with some speed v.
Okay.
Does that make sense?
Yeah.
Okay. Now, when I say the lab frame, that's, the lab frame is me standing here amidst these two wires. The current in this first scenario that we're considering is flowing in this direction, the drift velocity, the opposite direction. So I see the electrons going this way, I see the current going this way, yes?
Yeah.
This is the lab frame. Now, if you know anything about magnetism, you may know where this is going. But let me just ask you guys who don't know anything about magnetism, would we expect any funny behavior out of these wires when I do this experiment? Anything going to happen? Well, what you know so far about electrostatics, and even what we've talked about when we talked about currents, and Kirchhoff's rules, and Ohm's law, and all that stuff, nothing leads you to believe that anything funny would be going on in this laboratory, yes?
Yes.
So we're going to start with that position, that's all we know. We're going to pretend that we've never heard of the word magnetism, or magnetic field, or magnetic forces.
Right.
And let's see where we can go with this. So for starters, in the lab frame, we can say a little something about this. And one thing I want to note, right, is that there is a charge density in these wires, but in the lab frame, there is no net charge. Otherwise, if I were to pull a test charge out of my pocket and hold it up, it might be attracted towards one of these wires or repelled by it. But we're going to note that in the slab frame that we observe that there is no net charge density, no net charge. And we're going to write it like this. We're going to say that the lambda plus, and I'm not going to distinguish between wire 1 or wire 2 because I said they're the same, plus lambda minus is equal to 0. That means there's no net charge. Now another way to write that would be to move one of these to the other side of the equal sign here, and we could say that lambda plus equals minus lambda minus. And that's fine. So that's the first thing. But now I want to jump into a different reference frame. So I want to get into the reference frame of the electrons in wire 2. Remember, they're going this way with exactly the same speed as the electrons in the other wire. So that's our reference frame. E minus 2, the subscript 2 means wire 2, reference frame. Now, in this reference frame, because the currents are in the same direction, there is no relative velocity between my reference frame here in wire 2 and the conduction electrons in wire 1. You see, I'm kind of co-moving with them, okay, at exactly the same speed. So if I could look over and see electrons, and I'm riding on the electrons in this reference frame, I would look over at wire 1 and I would see the electrons stationary with respect to me. I'm moving along with it. This is different than the lab frame, yes?
Yeah.
But I know that there's a difference between the charge density that I would see in this reference frame. Well, let's do the positive charges first. That's, I think, easiest. The positive charges, who in the lab frame were stationary, right? They don't move, right? They're metal ions that are just sitting still, yes? Well, not really ions, but the way that we're thinking about them, we're separating them from the conduction electrons, which are moving, right? So these little positive charge centers are stationary in the lab frame. But in this new moving reference frame, if I'm going this way, right, then I see those positive charges going in the opposite direction at the same speed, yes?
Yeah.
Well, special relativity tells us, right, that moving reference frames, what happens to them? The lengths contract, yes?
Yeah.
So I would see the charge density. Let's see how I'm going to write this. Maybe I could put the plus up here for the positive charge, even though I wrote it as a subscript here, and put a 2 down here to indicate this is wire 2. Because let me point out, this is important. In my own wire, even though I see the positive charges in wire 2, of which I'm in, they are moving in the opposite direction, right? They're moving just like the positive charges in wire 1 that I'm observing, right? But I'm in that conductor, and this is a steady state current, right? There is no acceleration of the electrons in this wire because it's moving with respect to the stationary in the lab frame positive charge centers of the wire, right? Because they're all around you, right? I mean, you're part of the metal, right? But I'm not part of this wire. And so for this wire, I will see a different charge density than I saw in the lab frame. And we know how to account for that. It's just going to be, and we'll write, let me do it like this. We'll do lambda sub 2 plus. So that's the second wire. The plus means the positive charge centers, and then I'm going to put a prime on here, because remember, whenever we're in one of these moving reference frames, we like to put a prime on it to distinguish it from the lab frame or the stationary frame, yeah? This will be equal to gamma times lambda 2 plus in the lab frame. What is gamma? Does anyone remember gamma? I'll write it over here because we're going to be talking about it a lot. It's 1 over the square root of 1 minus v squared. It's v squared over c squared, but we're going to let c be equal to 1, as I usually do. It makes things a lot less complicated. If we need to put c's back in, we can figure it out just looking at the units, okay? So here, the velocity that we're talking about is something that goes between 0 and 1. Yeah, so speed of light is 1. This velocity can be anything between 0 and up to 1. Never equal to 1, because remember, nothing can travel at the speed of light except light and other massless things. Because we see those charges in a now smaller space, we see an increased charge density. Now the electrons, you might first say, well, because the electrons are co-moving with us, we don't see any there's no Lorentz contraction to do. But that's not entirely true, because remember that the lab frame, the electrons were moving. So we have to uncontract. So lambda 2 minus in this moving reference frame, right, is lambda 2 minus divided by gamma. Right? And the way to think of it is that here we're stationary, and so if we were to then get into the lab frame, right, we would have to multiply the moving frame's distance times gamma, so that in length contracts. So important thing to note there. So now we have two expressions, right? We're going to do basically the same thing we did here, lambda plus plus lambda minus, and see what the net charge is. In the lab frame it was 0. What is it here? So we'll call this lambda net prime is just equal to lambda 2 plus prime plus lambda 2 minus prime. But this is equal to gamma lambda 2 plus lambda 2 minus over gamma. But these two quantities are lab frame charge densities. And remember that lambda plus in the lab frame is equal to minus lambda minus. So we can rewrite this as equals gamma, the terrible gamma. Actually, I want to do it like this. I'm going to factor out this common factor of lambda. I'm just going to call it lambda, right? Lambda plus equals minus lambda minus, right? Call it lambda, the charge density, times gamma minus 1 over gamma. The important thing to note, though, is that gamma minus 1 over gamma is greater than 0. That means it's net positive. I'm writing some conduction electrons. Those have a negative charge. What do negative charges do when they experience a neighbor which is positively charged? What do they do? No. If I have a negative charge here and a positive charge here, what do they do? There's a word, attract. They attract. So in this moving frame, we see the electrons attracting. What's that going to cause the wire to do? It's going to cause the wire to move
Together.
Yes, this is a transverse direction. The velocity is this way. Well, actually, the velocity is this way. The force that we experience is going that way. If we go back to lecture 94, right, we will find that the electric field, remember this is a wire, right? It's a long straight wire, and I'm saying it has a positive charge, or a positive charge density rather. We will see the electric field was equal to lambda, the linear charge density, divided by 2 pi epsilon naught times the distance of separation between them. So let me mark that off here. The distance between the two wires we'll just call big R. So the electric field, if there is a net positive charge density in wire 1, will be given by this equation if the wire is long and straight. Well, force is just Q times E.
Yeah.
So that's just equal to Q times lambda over 2 pi epsilon naught times R. Now, in your homework, I'm going to ask you to derive an expression for lambda. And I'm going to write this as lambda net. In your homework, you will have to show that lambda net is equal to lambda times gamma times v sub d squared, where v sub d is this velocity, this drift velocity we've been talking about, okay? And so you can show that algebraically, just working with this, okay? And the definition of gamma, where you replace v with v sub d.
Yeah.
C is 1, remember. So if I substitute in with this, what do I get? I get Q, how do I want to write this? Times lambda, that's the lab frame charge density. Lambda plus and lambda minus are the same magnitude, different in sign. Actually, let me put the gamma in front, if you don't mind. Put the gamma in front, and I'm going to put lambda Q v sub d squared over 2 pi epsilon naught times R. I'm going to write this force up here. Force prime, I'll call it F prime, because we are in the moving reference frame. Because special relativity, right, says that the laws of physics in any inertial reference frame is going to be the same, regardless of which reference frame we choose. So if we see this transverse force in this moving reference frame, then we must also see it in the lab frame. And maybe we can just remember that when the currents are going in the same direction, we found that there's an attractive force between them. All right, I just want to switch gears now, and I want to change the direction of the current and see how that looks, okay? So it's a slightly different problem. So now I am going to reverse the current, but I'm going to stay in this moving reference frame of wire number 2, still writing the conduction electrons. The only thing that changed is that now the current is in the opposite direction. So in this frame of reference, we still see a relative velocity between us and the positive charge centers in wire number 1. They're still moving with a relative velocity of v sub d, but I want you to think of it like, I'll write a little train here, some plus signs on it, meaning that these are the positive charge carriers, and we still see it moving with some drift velocity.
Yeah.
But on board we have another train which with respect to them is moving with the same drift velocity relative to them, right? So this is a classic relativistic addition of velocities problem. And if you look at lecture 52, we talk about the addition of velocities, right, in special relativity. The 1 sub minus is the speed of the electrons in wire 1 will be equal to minus 2 v sub d divided by 1 plus v sub d squared. If it was Galilean relativity, it would just be minus 2 times v sub d. The minus is there because it's going in the opposite direction. But for drift velocities in metals are relatively slow. Call it something on the order of like 1/10 of a millimeter per second. Okay, it's very small. And so for such small velocities, we can approximate this as just minus 2 v sub d, which means that we're basically treating it like Galilean relativity. So the negative charge density that we will see actually increases because of this increased velocity. And so from this point of view, lambda 2 minus prime will look like, I'm going to call it gamma prime times lambda, the lab reference frame charge density. Because, well, I need to put a minus sign on it though, because, and here gamma prime is going to be 1 over the square root of 1 minus 4 v squared, approximately. The 4 is because of the minus 2 here, which got squared and turned into a 4. And this should be v sub d, by the way. Whereas the positive charge carriers were pretty much the same as before. Minus 2 plus prime will be gamma times lambda plus. And just so we have some comparison on the size of these things, just want to note that over here, the gamma is going to be approximately 1 plus 1/2 v sub d, whereas gamma prime is going to be approximately 1 plus 2 v sub d. Oh, sorry. It should be squared. V sub d squared, v sub d squared. Sorry. So this is just the approximation. These are the binomial expansion, or Taylor expansion if you know those, of gamma prime and gamma, which is just this term here, okay? So you can see the difference in these factors right there. So if I write lambda net, this will be lambda 2 plus times gamma plus lambda 2 minus times gamma prime, which making the same lab frame substitution where, since these are lab frame numbers, I can write lambda 2 minus as minus lambda 2 plus, but I'm just going to call those both lambda, and we'll get lambda times gamma minus gamma prime. This tells us that lambda net is less than 0. So this time it's negative because of the magnitudes of these two quantities, right? Gamma prime is the faster moving. And you can see that in these terms right here. If you do this minus this, right, you'll see that this is a negative value. So now we see we have a negative charge density. So what are the electrons that I'm riding on in wire 2 going to do when they experience this electric field from a negative charge density wire over here? Are they going to attract again? They repel. So this time we see a repulsion. Now if I were to plug this into the equation for a wire, again, the force term would be the same. The direction is switched, right, because of this Q here. So this is just the magnitude, right? The direction, right, we get from this charge density calculation. If it's a positive charge and if wire 1 is net positively charged, we'll see an attraction. If it's net negatively charged, then we will see a repulsion. Does that make sense? Interesting though, right? So it seems to suggest that in the lab frame we should see this same thing. That if we run electricity through wires in the same direction, we'll see them attracted towards each other. And if we run them in opposite directions, they will be repelled again, from each other. So, because this is what relativity says should happen. And sure enough, this is not how they discovered it by any means, but sure enough, people did discover this notion of magnetic forces. So how do we explain this in the lab frame? Well, we need a new law of physics, right? And that new law we will call the Lorentz force law. And this force law says something like this. It says, there is a transverse force, Q times the velocity, cross B. What is B? These are vectors, remember? B is this magnetic field. And we're going to talk about magnetic field in much more detail next week when we'll calculate the magnetic field in various circumstances. But for now, I just want you to think it's analogous to the electric field. The units, I guess I should mention the units. The unit of a magnetic field are Teslas, named after Nikola Tesla. And the way that it's defined is such that if you have 1 coulomb of charge moving at 1 meter per second, then it will generate a force that is equal to 1 Newton.
Yeah.
I think that's how it's defined. I have to double check, but. One Tesla is the base unit for magnetic field. It's actually a rather huge number. And so instead, we oftentimes use units of Gauss. And the Gauss is such that 10,000 Gauss is equal to 1 Tesla. Because Tesla is just a huge magnetic field. Most magnetic fields are really, really small. We don't want to have to say, 10 to the minus 5 Teslas is our magnetic field strength. We'd like to say 1 Gauss.
Okay.
For example, the magnetic field from the Earth, which you've probably heard about, yes, it's what makes compasses point the way they do. We'll talk about magnetic fields more later, but that is 0.6 Gauss. So it's about on the order of a Gauss. And 10,000 of those is 1 Tesla. So it's a rather large value for the field. You can see it's more complicated than, say, what you're used to, right? Where the force for electrostatics, right? The force is just the charge times the electric field. Here we've got this cross product. So what's that all about? Well, let me see if I can draw a good diagram here. Let's call this north, south. Why am I using north and south? Because we're talking about magnets, so why not? This will be the east direction, the west direction, right? These are orthogonal. I've just drawn them a bit funny. I'll put my little charge right here. We can draw a little dotted line. That's down. This is perpendicular to this. This is perpendicular to this. And let's say that it's traveling northerly. So it's traveling in the north direction. Yes. It's charge Q, traveling in the north direction with some velocity, V. And there is a magnetic field present. Let's put it at an angle like this, maybe. Here we go. Here's my B field. And it is making an angle of theta to this velocity. And let us imagine a little plane like this. So I've kind of cut out a little plane here. So I don't know if my drawing is any good, if you see what I'm talking about here. But we basically have the B field and the velocity making a plane. And the force will be perpendicular to that plane. That force will be in this direction, F. And the rule to figure out which way the force goes is you take your right hand, you curl the velocity into the B field. And whichever direction your thumb is pointing is the direction of the force. So all 3 of these things are perpendicular. Right, so if this is my velocity, if I'm going this way, right, and there's a B field, and it is, say, in this direction like this, right, you can figure out which way the force is by simply taking your hand and curling the velocity into the B field like you're going to try to squeeze them together like that, right? And whichever direction my thumb is pointing is the direction of the force. So if I turn it sideways, you can kind of see it like that. If I rotate it like this, see how the force changes? So you imagine this plane that's made between the velocity vector and the B field direction. You imagine this plane, and the force will always be perpendicular to that. It'll be a normal, if you want, coming out of that plane. So it's always pointing like so, you see?
Yeah.
And you may recall that another way to write this cross product, Q times the magnitude of V and the magnitude of B times the sine of the angle between them. So if the B was, to maximize this force, the B field would have to be perpendicular. The theta would have to be 90 degrees with respect to the velocity.
Yeah.
If the B field is in the same direction of the velocity, what's the sine of 0?
0.
0. The force is 0. There's no force if you're in the direction of the magnetic field. So if I have a magnetic field pointing this way and my velocity is in that direction as well, I experience no force. But as soon as I veer off into another direction, I suddenly feel a force and get pushed to the left. And a funny consequence of this transverse nature of the force is that you cannot change the kinetic energy of a charged particle with a magnetic field. You can change its direction of travel, but not its not the magnitude of its velocity. You see?
Yeah.
And I'll try to put, maybe I'll put a problem in the homework for this lecture on what's called cyclotron motion. It's also a non-conservative force. Now, for those that know, right, one of the consequences of the electric field being a conservative force, right, the electric force, is that we can write the electric field in terms of a scalar potential, whose gradient gives us the force, right? You cannot write a scalar potential for the magnetic field. It is a non-conservative force. Also, you cannot do any work with a magnetic field. You might recall that work can be written as the integral of f dot dr, where dr is a little displacement. The displacement will be in the direction of the velocity, right? Because it's moving, right? So imagine a little displacement. That's a little change. It'll be in the direction that it's moving, obviously. But that's perpendicular to the force, right? And so when we have the dot product, right, different than the cross product. It's not the sine of theta anymore. It's the cosine of the angle between them. I guess I could write this. This will be the magnitude of f times the magnitude of, I'm going to call it a delta r, right, displacement, times the cosine of the angle between them. Well, that's always 90 degrees. And so this will always be 0. So what I want to do now is try to connect this new force law with what we found from relativity. Probably in the next lecture, where we'll be talking about magnetic fields and how to calculate them, we will do a very common problem in magnetism, which is to calculate the magnetic field due to a long straight wire, much like we did when we did calculations for electric field from a long straight wire. Okay, and when we do, we will find the following. So B, we will find is going to be equal to something mu naught times the current divided by 2 times pi times r, where r is the separation, the distance of the test point from the wire. It's just like the r in our picture here, where we're thinking of this being, on any of the individual conduction electrons in wire 2 being our test point, yes, or our test charge. And so you can see some similarities coming out, right? Also, in this particular configuration, remember the force and the velocity, right? The velocity is this way, or maybe it's this way, right? Because we're the conduction electrons. And the force is this way. The angle of interest here is 90 degrees. So this will come out to be F is equal to, we'll get the Q, we'll get the V sub D, drift velocity, we'll get the mu naught, the current I over 2 pi r. The current I in, where this is the number of charge carriers per unit volume, times the cross-sectional area, times the drift velocity, times the charge. And so if I replace the current using this formula here, sorry, I need one more thing I need to add to this. I need to get the charge density right in here. The charge density is the number of charge carriers times the cross-sectional area times the charge. Does that make sense? Because this is a number density in terms of volume, right? It's the number of charge carriers per unit volume times an area. That gives us a linear charge density, number of charge carriers per unit length. I can rewrite the current as the linear charge density times the drift velocity. And so I'm going to replace I in here. I'll write it down here. We get Q, V sub D, mu naught over 2 pi r. I will be lambda times the drift velocity. But look, we have it twice, right? So we need to square the drift velocity, yes? You see that? And everything it's starting to look a lot like this, except we have a mu naught. This mu naught is just like epsilon naught. It's this physical constant which has to do with it characterizes how well free space permits the presence of fields. If it's an electric field, it's epsilon naught. If it's a magnetic field, we call it mu naught. So this is a constant that really has to do with magnetism. I'm going to move it outside over here. Move this over here. There we go, lambda. I'm going to put the mu naught right here. And I'm kind of jumping ahead here, but Maxwell, right, after he unified the laws of electricity and magnetism, Maxwell found that when he worked with the laws of electricity and the laws of magnetism, he could create a wave equation. Right? And we've looked at wave equations before, and we know that wave equations have wave speeds, yes? And he found that the wave speed for his wave equation, using the laws of electricity and the laws of magnetism, looked like this. It was c squared was equal to 1 over epsilon naught times mu naught. So the wave speed squared was equal to 1 over epsilon naught times mu naught. Physical constant for electricity, physical constant for magnetism, and the number that you get when you multiply these physical constants like this is the square of the actual speed of light. People knew what the speed of light was back then, at least roughly. And so this is what made him kind of propose that light is this, electromagnetic wave, okay? Yeah. Because his wave equation, which he was able to generate, had its speed given by these physical constants, which were well known in the field of electrostatics and magnetostatics. So he made this connection between the two. But anyway, we're going to use this identity here, right? Remember, we let C be equal to 1. So this is really saying that 1 equals 1 over epsilon naught mu naught, which is another way we could write this as mu naught is equal to 1 over epsilon naught. So if I do that, here, what do I get? I get Q times lambda times V sub d squared divided by 2 pi. Mu naught became 1 over epsilon naught, so I'll put the epsilon naught right here, R. Does this look similar to this? Compare these two. So F in the lab frame is equal to Q lambda V sub d squared over 2 pi epsilon naught R. You see the similarity? What's the difference, right? We see F prime is just equal to gamma times F. It's like a Lorentz contraction of, what's a transformation? It's a relativistic transformation nonetheless, right, of the force in the lab frame to get the force in the moving reference frame.
Yeah.
It's got that relativistic gamma in there that connects them. So that's the reason for the title, the relativistic origins of electromagnetism, or of magnetism. Electricity and magnetism, whether it's an electric field or a magnetic field, it all kind of depends on your reference frame. They're really aspects of the same thing. If I had chosen my velocity, my reference frame to be different than the drift velocity of the electrons, right, I would get some mixture of electric field and magnetic field that I would experience, you see?
Yeah.
But I chose them the way I did because at this point we had not yet encountered magnetic fields. I was motivating their presence by showing you that conducting wires should produce forces that cause them to bend in or bulge out from each other, just using electrostatics and relativity, which means there's a missing law. I then show you that missing law that allows you to calculate what that force is going to be in the lab frame. It's called the Lorentz force law. And this is why we call it electromagnetism. It's really one thing. It's not that there are electric fields and there are magnetic, and a completely different thing is the magnetic field, or that there are electric forces and unrelated magnetic forces. They are the same thing. It's all a matter of the reference frame that you're in, which description you use. This, if you go back and you find Albert Einstein's first paper on special relativity, this is the opening line in his paper, right? I think he called the paper something like on the electrodynamics of moving charges or something like that. That's what he was thinking about. You know, with these kind of observations, the similarity between electricity and magnetism, which everyone had kind of written off as just a coincidence, he took it seriously and showed that they were connected more intimately. I do want to add one last little bit here, in that I want to write the Lorentz force law in a complete sense, right? Because like I said, electromagnetism, it's one thing. And so the Lorentz force law gets both of them. It's Q times E plus Q times V cross B. If you wanted to, you could factor the Q out. Okay, so we have two terms. If you're in a reference frame where there is no electric field, then it's just this. If you're in a reference frame where there is no magnetic field, then it's just this. So in our case, when we got into the reference frame, it was co-moving with the conduction electrons in wire 1. We only saw this part of it, right? But we didn't see any of this when we were in the frame of reference where this was 0, because it was all in this term, you see? Does that make sense? Yeah. So, any questions regarding what we've talked about here? Yes? No? Got it? Easy? Surprising? Yes?
Surprising.
Somewhat, yeah, it is surprising, right? It's a pretty big deal, right? We haven't talked about magnetism at all, but I mean, people have known about magnetism, right? Lodestone, right, for thousands of years. And I haven't explained at all how this is connected to magnetism and materials. Magnetism is about moving charges. And so from what I've said here, you should not suspect this has any connection at all to materials like rocks or refrigerator magnets, because your question would, of course, be, where are the moving charges? You said magnetism is about moving charges. But we'll get to that. We'll talk about where the moving charges are in refrigerator magnets and things like that. That's it. Next time we'll talk about calculating magnetic fields in various circumstances. And one last thing I'll mention, if you really want to dig in deeper on this material, there's a nice discussion of this kind of stuff in Feynman's Lectures on Physics, Volume 2, Chapter 13. What I did here is a little bit different than what he was doing, but it's pretty much the same thing. So, but he gives a nice discussion and motivation in there if you're interested. So you can find that for free online. I don't know the website, but I can put a link. And that's all I got for you. Okay.